There's an agency, like they're all here for maintenance. How many? So I think one of I was very smart and I will be. Yeah.
All right. Okay, so our calendar, we're going to spend today starting our next unit. Obviously, this next unit is not going to be on tomorrow's test. Tomorrow's test is just covering limits. So there's two packets. One is the notes packet, and the other are the exercise pages from the textbook. There's homework tonight, but I won't check that till Friday. Okay, so tonight I want you guys to focus on studying for tomorrow's test. I will have a help session tomorrow, but I'm not going to create a new worksheet for you. So I encourage you guys to review through your the major test review worksheet that I did, and then use the additional sheets as supplement for additional practice. And look over your notes, look over your homework problems. Okay, but I'll send out a reminder this afternoon, and you can come in. I'll be available starting at 7:15 tomorrow. So, okay, no calculators on the test tomorrow, and close notes. Okay. So let's go to page 1 here. So here's our goal. Our goal is to discover a formula to calculate the slope or steepness of all tangent lines to a curved graph. So we call this, so here's a tangent line. This is a tangent line to a point on the curve of f of x at point P. So the special relationship between tangent line and the curve is that the curve and the line will not only share the same point, they will also share the same what? Slope. That's right. So the tangent line is going to share the exact steepness of this curve at this point. So our goal is to try to figure out, how do we find the formula for this tangent line? The issue is that if I want to find the slope of a line, I need 2 points, but a tangent line only has 1 point on the curve. So we can start off with something called a secant line. A secant line will allow us to find that slope, because our slope formula is change in y over change in x. And because we have 2 points, we're able to get to the slope of that line. Yeah. So the issue, however, is that because we are unable to find the slope using just 1 point, we need 2 points. We're going to be working from an approximation standpoint. Right? So the slope of a secant line is a very rough approximation, at least at this point, of the tangent line at point P. Right? We see that this secant line maybe has a slope of like 2, and maybe this tangent line has a slope of 1/2. But we know it's obviously different, right? They're both positive slope, but we can obviously tell they're different. And the hope is that we can improve the slope of the secant line by moving that point Q closer towards point P. Right? So that's what we're going to be kind of exploring today. So here I have in this diagram where I have these different secant lines, and you can tell that if I move my point Q closer towards point P, that secant line is going to get closer and closer to look like the tangent line. Okay. So if we can improve the approximation by moving point Q closer towards point P, then what if we just continue to move it closer, right? So maybe we can get it out of approximation. So that's going to be the concept that we're going to be exploring, okay? We're going to use limits to decrease the distance between point P and point Q until that distance is 0, okay? And this process will improve the approximation of the secant line slope until the value becomes the exact slope of the secant, the exact slope of the tangent line. Okay. So go ahead and spend a minute to copy that down. So give you guys a minute to copy those things down. So we know the slope of a secant line, right? Change in y over change in x. But what we're going to do is we're going to have to introduce a different variable to allow for that point Q to move closer towards point P. So we're still going to go through a slope formula, but it's going to look a little messier because we're going to introduce another variable that will allow that point Q to move. Okay. Okay, so point P is still going to be x1, y1. Point Q is still x2, y2. But let's go down to this bottom diagram here. Okay, so let's say that point P is some x distance away from the origin. So I'm going to call this point x value. And if I plug x into the function, then I'm just getting f of x. I'm just getting the y value associated with that point P. So then point P is x comma f of x. I'm leaving it in function notation to give it that flexibility for whatever x value I put in, I can find that appropriate y value. So this is my x1, y1. Right. Now, point Q is going to be some distance away from point P to the right of point P. And I'm going to call it a distance that is h units away. So the distance between x and the next value is h distance away. So this point is simply just x plus h. Okay. Maybe I could have just said, oh, that's the distance of 3 or 4 or 6. But the problem is if I just give it a constant value, then I'm unable to move it, right? So that h allows me to give it that flexibility to eventually move it closer. So if x plus h is the x value of my point Q, what can I use to represent the y value of point Q? F of x plus h, right? So that just represents whatever x value this point is. I'm going to insert that x value into the function, and then that y value ends up being f of x plus h. So I'm going to let that be my x2, y2. So using the addition of that h, I can still find the slope between these 2 points, right? So what would the slope look like using those notations? How would you represent slope? But instead of that, we'll use f of x plus h minus f of x all over x plus h minus x. So this is the slope formula adapted using that h variable. Okay, what else can I do to clean this up? Yeah, x is canceled out, so I'm just left with h. Yeah. So we're going to add that h approaches 0 in front of it to give it that flexibility, right? So now if I can get that h to decrease, but not only decrease to a small number, I'm going to make it decrease until there is no distance between point P and point Q. So the idea is that, well, I know I need 2 points to find the slope of a line, but what if I can decrease that distance of point H to be 0? If that value of H is 0, then point Q and point P will essentially become the same point, and that means we can find the slope of a tangent line, a line with only 1 point instead of 2 points. Okay, so we're taking the restriction from the restriction of the slope formula, and we're adapting it so that we only need 1 point. Okay, and that point is going to be this point P, and this point P will allow us to find the slope of this tangent line. Okay, so that's how we're able to work around the issue of slope requiring 2 points. Okay, so we call this the derivative formula here. So f prime of x is a notation for a derivative function. And this is basically just a more robust version of a slope formula, right? This allows us to find the slope of a tangent line instead of relying on just an approximation of a secant line. And obviously, if I pick the point really, really close to point P, I can still get a very good approximation, but it's never going to be the exact slope of the tangent line. Okay, so we're going to be working under this general limit definition of a derivative, but we're also going to discover this alternate limit definition of a derivative. They both kind of have a slope look to them, but then the alternate limit definition has a bit more of that slope feel to it. You get that y2 minus y1 over x2 minus x1, more apparent than this one, right? This one, it had it, but then that denominator canceled out, will reduce to be just that h. But whenever you see this, I just want you to connect this with the concept of slope, right? We're just adapting the slope with that h being able to move, being able to change. Okay, so a derivative is the slope or steepness of a curve at a single point, and the derivative function is a slope finding formula for a curved graph where the slope of the curve is ever changing. Okay. So let's go to the next page. Okay, so page 2. let's say we're starting off with a function y equals x squared. Okay, we know that's a parabola that goes through the origin. If I asked you what is the slope of a line, you would just figure out, changing y, changing x, find the slope. Once you find a slope of that line, then that slope is going to be the true for every point on that line, right? So if I ask you for a slope of a line, you will give me a constant and it will never change. But if I ask you what is the slope of this curve, then you would say it depends, right? I mean, at a point, it could be a negative slope. At another point, it could be 0. At another point, it could be a positive slope. There's no single point where the slope is going to stay consistent, right? It's going to be an ever-changing value. However, we can create a slope formula that will tell us the slope of every point on this curve using this general definition or general limit definition of a derivative. Okay, so we're going to work with this limit definition here, and then later on we'll explore that alternative limit definition in a second. Okay, so we basically want to get this numerator out of function notation. So we're going to build that f of x plus h. Okay, so first is okay, so this function is x squared. So my f of x is x squared. I like to do this. If it helps you, that's great. Is create a function with reserved spaces for that x, and that way you know exactly where that x plus h goes. So x plus h is going to be the new argument that gets inserted into the function. So we have the appropriate replacements for my numerator of my limit definition. I basically just want to get this out of function notation. So f of x plus h is now just that x plus h quantity squared, and f of x is simply just the x squared. So we're just going to treat this like a limit problem and go through our steps involving limits. Sorry. I already want to get it out of function notation. So here's my f of x plus h, which is x plus h squared, minus f of x all over h. Okay, so we go through our limit procedure. We're approaching a real number. We evaluate, confirm that we're getting 0 over 0. And then we go through our expansion step. We're looking for an h that is hiding in the numerator because there's a hole that we can remove to allow for us to reevaluate. Okay, we see some like terms we can combine. Okay, what can we do with the numerator here? We see a common factor. Yep, factor in h. Because we know the h is what's causing that hole to show up, right? So we can factor that h out. Sorry, there's a 2x plus h here. Okay, h is canceled out. Okay, we reevaluate the limits. And now replace any remaining h's with 0. So then we get 2x plus 0, which is 2x. So this is the slope of this curve. Okay, so that x basically is telling us that there is a change in the slope of this curve based off of this pattern, this 2x. Okay, so I just want to convince you that this does work for this curve here. What's the x value here? 0. What do you expect the slope to be just by looking at this graph? 0, right? So if I insert 0 in for my derivative or my slope formula, I should get a 0 in return. So 2 times 0 is 0. Okay, so that is a slope 0, right? Let's say I chose this point here. Let's say I chose 1. What do you expect from this slope here? You expect a positive slope, right? Some positive slope. So if I insert 1 into the derivative, I should get a positive slope as well. 2 times 1 is 2. Okay. As I move further to the right, my slope is going to become steeper and steeper, right? So let's say I plugged in 5, right? If I plug 5 into the derivative, I should get a pretty steep slope. 2 times 5 is 10, right? So we see that pattern. How about the left side? All these values are showing me a slope of what? Negative, right? Different variations of negative. So let's say I chose -4, right? -4, I'm expecting a negative, rather steep negative slope. So if I insert 4 into the derivative, I'm going to get 2 times 4. Sorry, 2 times -4 is -8, right? So anything on this curve, we can kind of visualize and convince ourselves, you know, that it makes sense visually. Okay. So part B says, or sorry, yeah, part B here says, write the equation of a tangent line to the graph at x equals 1. So if I want to find the equation of a line, I need an order pair and I need a slope. So to find my order pair, I'm going to use my function. To get my slope, I'm going to use my derivative. Okay. So I'm targeting x equals 1 here. So what's my y value? 1, right? F of 1 is 1 squared, which is 1. And then what's f prime of 1? What's the slope? F prime of 1 is 2. So you have your order pair, you have your slope. Now you can build your tangent line equation. Sorry, yeah, your equation, which is your tangent line, which is going to be this line right here. Okay, any questions? Okay, so the big takeaway here is that your function is going to tell you the location of your order pair of your y value, and then your derivative is going to tell you the steepness of that point on that curve. So let's try part C. Part C says, write the equation of the tangent line of the function at x equals -5. So imagine there is a tangent line that is skimming the surface of the graph at x equals -5. We're going to find the equation of this line here. So same idea. You're going to take your -5, find the y value using your original function, and you're also going to use that derivative to help you find the slope at that point. And then again, once you find your order pair and your slope, you can write the equation of your line. Okay, try part C. All right, same equation, same derivative equation, same function equation. We're still talking about the same graph here. right, so again, this is a representation of what that line could look like at that order pair, -5, 25, with a slope of -10, and this is the equation of that line. Okay, so to recap, a function is a height finding formula, basically finds the y value of that graph. Since f of 1 equals 1, this tells us that when x equals 1, the height of the graph has a y value of 1. F prime of x is a slope finding formula for the f of x graph. Since f prime of 1 is equal to 2, that tells us that at x equals 1, the slope of the tangent line to that curve has a steepness of 2. So a function and derivative, they both refer to the same graph, but they're giving you different information about that graph. One is giving you a location, the other one is giving you the rate of change or the steepness at that point. Okay, any questions here? Okay, so we're just going to explore different variations, different types of functions, but still practice a bit more with this general definition, general limit definition of a derivative. Okay, so let's go to the next page. Okay, so try example 2. You have a different function, a radical function, but you're going to adapt it so that it can fit in the numerator of this limit definition. So we have to find a suitable replacement for f of x plus h for this particular function. So I find that's a nice way to make sure you don't make a mistake. So that you're able to put that x plus h in the correct spot is create a set of parentheses where the x is for your original function, remove the x, and then that way you have those parentheses, and those parentheses will be your reserve space for your x plus h. So it's basically going to replace every x that you see in your original function. So now that we have the f of x plus h out of function notation, we can start putting it into the limit definition of a derivative. And then once you get it set, then you're just going to treat it like a limit problem, right? Direct substitution. Realize there's a hole, go through your appropriate steps. In this case, it's going to be a conjugate method. But your goal is to find the hidden h in the numerator, because you know that it's the h's that's causing the numerator denominator to give you a 0 over 0. So you're always going to be able to identify that h. And then once you get that h to show up in the numerator, you can cancel between your numerator and denominator, reevaluate, that will get you to your derivative formula. So once you confirm it's 0 over 0, we know that this particular problem, we can resolve those radicals by multiplying by the conjugate. So expand the numerator, but leave the denominator alone. Once you expand that numerator, the radicals go away, the x's cancel out, you're left with an h over h, which cancels out nicely. Once you have your reduced expression, replace any remaining h's with 0, and you're left with a derivative in terms of x. So the 1 over 2 root x is going to do the job of finding any slope of any point on this radical function, on this square root of x function. Any questions so far? Okay, so then we have the necessary formulas to answer part B. Part B says write the equation of the tangent line of the function at x equals 2. We have our function, which will take us to the y value. We have a derivative, which will take us to the slope, and one slope form. All right, so my slope is, well, my y value is √2. My slope is 1 over 2 √2. It's okay, again, to leave radicals in the denominator. Okay, AP, College Board, they don't care if radicals in the denominator. So you can choose to rationalize or choose not to rationalize. Either is fine. So this is my slope. My slope is 1 over 2 √2. Now, if you look at the graph, this is what radical function looks like. You can tell that the slope of this graph is kind of gradual, right? It's not a very steep curve. So we can imagine, kind of figure that the slope should be a pretty small number as well. And we see that's the case here, right? 1 over 2 √2 is a number that's smaller than 1. And so it's still a positive slope, but it's not a very steep slope. It's a very gradual slope. So that matches up with what we know to be true about the radical function. Okay, so the other definition is this alternative or this alternate derivative definition, which is at the top of the page that you see here. So if you look at these two, they both have limits involved, but they look a little different. There's no h involved with the alternate limit definition. And it also visually feels more like a slope formula, right? Change in y or change in x. The main difference is that this alternate definition will take you directly to the slope value. So it'll just take you to the slope value without it stopping midpoint to give you the formula. Okay, so it's not going to stop at a formula and then you evaluate that formula to get to the slope. It's going to take you directly to a numeric slope value. So I want to show you how that works. So let's look at example 3. I'm going to copy down that formula so that we can see it right when we're going to use it. Okay, so the first thing that you want to do with the alternate definition is go ahead and do this here. Underline all the C's that show up in the formula. Okay, that is the point that you're working with, and they're always going to provide you a point in question. Okay, so here the center of our problem is at x equals 2. So that's our C value. Our C value is 2. So go ahead and do this. Replace every C in the formula with 2. And then things will become more clear as to what your next step will be. So the similarity with the general definition is that just like the general definition, we're going to do some work to replace the numerator because the numerator is not ready for us to do any algebraic work because it's a function notation. So the similarity is that the numerator needs to be adjusted. We need to get it out of function notation. Okay, so what can I replace f of x with? Yep, square root of x. Okay, good. What can I do to find f of 2? Yeah, plug 2 into the original function, right? So what's f of 2? Square root of 2. So there's my replacement for f of 2. Okay, so now I'm just going to get the numerator out of function notation. And once I do that, then it just becomes a limit problem that we can go through our steps like before. Right, so first things first, direct substitution. Convince yourself that there's a hole before you go through with the conjugate method. So we do see that this limit is going to give us 0 over 0. We know there's a hole. And that x minus 2 is also very helpful because we know that there's an x minus 2 hiding in the numerator that we're trying to pair up with the denominator to cancel out. So let's go through our conjugate method, multiply numerator denominator by the conjugate. Expand the numerator, but leave the denominator in factored form. The x minus 2 in the denominator is ready to go. We don't want to lose that. So the numerator expands out to be x minus 2. The middle terms drop out. X minus 2, that's a perfect match with that x minus 2 in the denominator. We reduce. There's a 1 that's going to remain in the numerator, where our reduced expression is now 1 over root x plus root 2. Replace every x you see with root 2, and then 1 root 2 plus 1 root 2 is 2 root 2. So that's my slope. Right. And as you can see, it's the same slope that we got above, right? So we're finding the same slope, just wanted to show you 2 different ways to get there. And also how it's getting to the answer a little differently. The limit definition, the general definition I find to be more flexible, because if you go through the formula, once you get that formula, you can use it to find any slope at any point. Here, once you lock into a point, it's going to get you that slope. And if you want to find the slope at a different point, you got to go back to the very beginning and plug in like 3 or 4 or 5. So it's not as adaptable. But really the purpose of these 2 definitions is twofold. One, for us to see that connection between slope and derivative. Because after this, we're going to have a much more efficient way of getting to our derivative, but it's also more abstract. We're not able to see that slope connection as well. Here, it's a little bit more tedious algebraically, but we're able to see that connection with slope a lot more clearly. The second thing that's important about these 2 definitions is that on the AP exam, you're not going to be quite asked to find the derivative from scratch using this method because we have a much more efficient way. But what you may have to be able to do is to look at something that is in this derivative definition or this limit definition and be able to pull out what it's asking you to do. Okay, so I'll show you a little bit of what an AP format question could look like on Friday, so we can kind of make that connection between these 2. But ultimately, it's more conceptual with what we're doing here. But knowledge of these 2 definitions is still going to be important for the AP exam, even if we're not using it the way that we're using it here. Okay, let's do some, let me go through a vocabulary here and then we'll do some more practice with the general definition. Okay, so differentiability. So differentiability, in order for a function to be differentiable, so differentiable just means that that a derivative or a slope is able to be found. So visually, what differentiable looks like is a smooth curve. So if I can see a smooth curve in front of me, that means the slope can exist at every point on that curve. Okay, so that's what differentiable means. So if a function is differentiable, then the graph has to be continuous at that point. It cannot have a sharp turn, and it cannot have a vertical tangent at that point. So here, a cusp, a corner, a sharp turn, the slope is undefined at this point. Okay, so that's an example of a function that's continuous, but it's not differentiable because of that sharp turn. So my f prime of A would be undefined or doesn't exist. I can't draw a tangent line to a sharp turn. Second, this is more obvious, discontinuous. So if I have a hole, if I have a jump discontinuity, if I have a vertical asymptote, if my function is discontinuous, I'm unable to find the slope at that point. Okay, so f prime of A is also undefined at A. And then finally, vertical tangent. So vertical tangent is a graph where it's going to slope down for a moment, but that steepness is going to be exactly a vertical line. And if I draw a tangent to this curve, it ends up being a vertical line. And we know that the slope of a vertical line is undefined. So if there is a vertical tangent, then we also consider that as a place where the slope is undefined. It may be continuous, but the slope is undefined at that vertical tangent. Okay, let's see if we can get some more practice, a little bit more practice with the general definition. So I just want us to try on the next page, 1 and 2. So under classwork examples, try 1 and 2, go through your steps, make sure you can build your f of x plus h correctly, because if you can do that, then you're just substituting and then you're just going through your steps of evaluating limits algorithmically. Okay, so page 4. See if we can do 1 and 2. Once you get your numerators replaced and out of function notation, make sure you go through direct substitution first, right? Convince yourself it's a 0 over 0. But once you do that, you're always going to be able to have an h in the numerator that will appear for you to cancel out. So if you're unable to get an h to factor out or an h to appear in the numerator, something went wrong in your algebraic step. Okay, so you want to make sure that you can either get an h by itself, or you should always be able to factor an h from the numerator to match with that denominator, which is causing that hole. Now, this is a linear graph, right? A linear graph has only one slope. And you can just tell by looking at this equation here, what's the slope of this line? Y equals mx plus b. The slope of this line is just -6. So we should get a consistent value there. So here, there are no x's that remain because the slope of this line is just -6. But as soon as you introduce a curve into your equation, then you're going to have x involved in your derivative because any point on that curve has an ever-changing slope. You're good with 1, go to number 2. Keep in mind, every x is going to get removed, and in place of the x is going to be an x plus h. So the initial set of parentheses I created there is just a way to make sure that I don't put the x plus h in the wrong spots. If I have a reserved spot for the x plus h, then I'm not going to make a mistake because there's only one place they can go. Now, once you clean up as much as you can in the numerator, make sure that every term is going to have an h attached to it because we're always going to be able to factor an h out. So if you somehow have a term that has no h's and it did not cancel out with something else, that means something went wrong. Okay, so if you're not able to factor an h out, you may have maybe you forgot to distribute a negative, maybe you expanded incorrectly. So just go back and look, right? That's a good way for you to see if you're on the right track or not. If you cannot get an h to appear in the numerator or factor out the numerator, we should be able to always get there, right? Especially if we're getting a 0 over 0. If we're getting a 0 over 0, we know there must be something between the numerator and denominator that matches, and it's always going to be the h because there's always an h in the denominator. Okay, any questions? So once you have your h's removed, you're going to reevaluate your limit, but you're just going to replace any remaining h's with 0 and see what's left over. And if you're starting off with a curve, you should end up with a derivative that has an x in it. Okay, so you guys have homework tonight, but I'm not going to check this homework until Friday. Tonight, I just want you guys to focus on studying for your test. Look over your notes, look over your homework, look over your study sheet. Again, I'll be available tomorrow morning at 7:15. If you have any questions, if you want me to go over any specific problems, but I will not have a new worksheet for you. Okay. All right, come get your phones.